In this video, we use the integrated rate laws to derive relationships that allow us to determine the half-life of chemical reactions. Now, we've seen this table a couple of times now. It's a table that summarizes some of the important relationships associated with reactions of different order. In this video, we focus on the bottom line of this table, which refers to the half-life of chemical reactions. Now, the half-life of a chemical reaction, or T-half, is the time required for the concentration of a reactant to drop to 1/2 its original value. The half-life refers to a time interval, and so the SI unit for half-life is the second. However, with many chemical reactions taking place over minutes or hours or even years, it's not uncommon to see the half-life quoted in these other time units. The half-life is a convenient way to express how fast a reaction proceeds. Fast reactions are characterized by a short half-life with small T-half values and large values of the rate constant. Slow reactions are characterized by a long half-life or large T-half values and small values of the rate constant. We can use the integrated rate laws to readily derive expressions for the half-life of zero, first and second order reactions by considering that the half-life is defined as the time taken for a reactant to drop to half of its original concentration, and so we can set AT to be equal to a half of A0 and substitute this value into the integrated rate law expressions. So for example, we'll start with the half-life for the first order processes first, which are the most common and most important. So the integrated rate law for a first order reaction can be written like this, but we also know that this equation can be rearranged to a more convenient form shown here. Now, given that at the half-life of a reaction, the concentration of A equals half its original concentration, we can make the appropriate substitution to get this expression here. Now, the left-hand side of this expression simplifies to ln2, or the natural log of 2, and solving for T-half, we get T-half equals the natural log of 2 on K, or T-half equals 0.693 on K. Now, since the rate constant K is a constant at a given temperature, we see that the half-life for a particular first-order reaction is also a constant at a given temperature. In other words, at a given temperature, the half-life of a first-order reaction is independent of the initial reactant concentration and only dependent on the value of K. This means that for a first-order reaction, the half-life remains constant throughout the course of a reaction. So, for example, if we consider first-order reaction where reactant A is converted to product B, if we were to start with an initial concentration of, say, 1.6 molar, and that concentration were to drop to 0.8 molar after, say, 10 seconds, we would then say that the half-life of this reaction is 10 seconds. For a first-order reaction, if we wait another 10 seconds, which is the time period equivalent to the half-life, the concentration will drop to 0.4 molar. And if we wait another 10 seconds, or if we wait another half-life, the concentration will drop to 0.2 molar, and so on. In other words, it doesn't matter what concentration we start with, the half-life will always be the same. Now, that's not the case for a second-order reaction, where we see that if we make the same substitution, we get an expression for the half-life that is dependent on the initial concentration A0. Doing the same for the zero-order case and making the appropriate substitution, we get the half-life being equal to the initial concentration divided by 2K, or 2 times the rate constant. In both cases, we see that the half-life is dependent on the initial reactant concentration, A0, and will therefore change during the course of a reaction as the concentration changes. In the case of a second-order reaction, the lower the initial concentration, the longer the half-life. In the case of a zero-order reaction, the greater the initial reactant concentration, the longer the half-life.